As we mentioned in an earlier section in this chapter, one of the big questions that calculus is designed to answer is about rates of change, specifically instantaneous rate of change as opposed to a rate of change over an interval. So that's what we're going to look at today. And so first we have this example where we have a man's height that's recorded over number of years. And we can see that this is definitely not a linear function. Okay, kids grow slower, faster, depending on how old they are, that kind of thing, and then kind of level out by the time they're adults. If we are looking for the average rate of change over an interval, then we're talking about the slope of what is called a secant line. Okay, and anytime you hear the words rate of change or slope, you should automatically think of the other one. So if we're talking average rate of change, that's going to be slope of a secant. In the other direction, if we have a function, does not have to be linear, but then we have the slope between 2 points on that, in other words, the slope of the secant line on that curve, then we should be thinking about average rate of change. Okay, so it's going to be helpful to remember slope and rate of change together, because a lot of times you'll be presented information given one of those terms and then asked to interpret it as the other. Okay, so we're talking about average rate of change over an interval. We find the slope between the two endpoints. So in this case, from year 13 to year 18, okay, the man's height increased from 57 up to 76 inches, and then that happened over a period of 5 years. Okay, so from 13, let's see, so from 57 up to 76, that's going to be an increase of 19 inches, and then from 13 to 18 is 5 years. So we end up with 19 over 5 inches per year. Another thing I want you to pay attention to here is the units. When we say 19 over 5, that's a change. So let me write up here. The 19 over 5, that's a change in inches over a number of years. So that's why our unit is inches per year. Okay. Anytime we're talking about a slope or a rate of change, your unit should be a rate unit as well, meaning usually distance per time or something else per time, something with respect to time. Okay, now let's say that we want to look at the instantaneous rate of change. Like we want to know how fast is the man growing at exactly, let's say 13 years. Okay, so if we're talking about at exactly 13 years, we would be talking about the slope of the tangent line, which I'm going to draw right here. Is actually, it's pretty close to that secant line. Let's zoom in here. Draw that again. Yeah, actually, it looks kind of close to where that secant line is, but we're looking for the slope of that line. Here, we're only intersecting at 1 point instead of intersecting at 2 points, so we can't do the slope between the two endpoints, okay? We're going to get to how we solve that in a second, but for now, we're going to talk about how we would approximate the slope of that line, or the rate of change of the function at that instance. So here it suggests, well, let's find the slope of some other intervals containing 13. And you don't have to use these, but here they suggest from 13 to 17, 13 to 16, 13 to 15, 13 to 14, 13 to 13 and a half years, 13 to 13.01 years, and we should get numbers that are getting closer and closer and closer to the instantaneous rate of change at 13. Likewise, we could pick points from the other side. We could say like from year 12 to 13, from 12 and a half to 13, from 12.75 to 13. And again, we have the same idea that we talked about with limits in the previous section, where we get closer and closer and closer to just at that instant, okay? So when it says what limit is approached by these computations as the shrinking interval of time gets closer and closer to the instant, really it just means we are getting closer and closer to an instantaneous rate of change, or in terms of the graph, we'd call that the slope of the tangent line. Okay, so a tangent line is a line that intersects a curve at exactly 1 point. Now, could this line, let's zoom back in here for a second, the way that I drew this line, technically it does intersect again elsewhere, but that doesn't matter as far as calling it a tangent line, because at this point, at time 13, it is a tangent line, okay? Let me draw one over here where things aren't quite as crowded. So here, I could draw a tangent line that passes through, what year is this? Year 5, okay? So something like this. And the slope of this line, the slope of this tangent line is the same as the instantaneous rate of change or slope of the function at time 5, okay? But I'm only actually intersecting the curve or the function at that one point, as opposed to saying, let's approximate the rate of change there by going from here to here and doing a secant. Ooh, I don't know what happened there. Ooh, I don't know how it changed to an arrow. Okay, a secant line like that. Okay, zoom back out here. All right, so once again, when you hear rate of change or slope, you should think of the other one. So if you hear instantaneous rate of change, you think tangent or slope of the tangent, or vice versa, and then average rate of change corresponds to the slope of the secant. Okay, so let's look at something that is going to be a little bit better visualization of this instantaneous rate of change. So I'm going to hop over to this. Get it in the window. Okay, so right here I have a function, just some generic f of x curve, and then I have a point P. The ordered pair for point P is c comma f of c for some number, which happens to be sitting at 3 right now, but I could move that point, and you can see it kind of moves along the curve as I do that. Okay, so I have a point P here. And then I'm going to draw a tangent segment at point P. Once again, if I move C around, if I move C around, that black line there stays tangent to the curve, okay? Stays tangent to the curve at any of the points, where C goes, okay? It's gonna be the same as, the slope of this line is the same as the slope of the curve at a point. Now, the formula for finding the rate of change of the tangent line comes from finding the slope between 2 points, because that's what slope is. So I'm going to define a second point, point Q, that's just going to be some distance away from C. Now, the way I've drawn it, it's over to the right, but it really doesn't have to be. I could have it some point over here, okay? But right now, my secant line between point P and the new point Q, it really is not related to the slope of the tangent at point P, okay, because Q is pretty far away from P. But Q is defined in terms of its distance from P horizontally. And that distance here we use the variable h for, okay? And we're going to get to a difference quotient that probably feels familiar because we have seen it a couple of times, okay? But h represents the distance between x equals c and x equals c plus h, okay? And then we want to look at what happens as h gets smaller. So I'm going to shrink h, meaning I'm going to move point Q closer to point P along the function. So look what's happening with the slope, and you can either look graphically or you can compare these numbers. As h gets smaller, point Q gets closer to point P, and our secant line, the green one, gets closer and closer and closer to the tangent line. And right here, I am very close, okay? It almost looks like the green line is right on top of this black segment, and I can see that the slopes are very, very, very close. So really what we're doing is we're saying what happens if h gets really, really close to 0. Let me do this. Now, oh, well, I thought I was going to stop. 1 second. Here. If h is equal to 0, what you'll notice is that the green line disappears. Well, why does the green line disappear? Because the green line is defined by 2 points, but the slope formula between 2 points, if those 2 points are in the same spot, is just 0, because I have y2 minus y1, well, they're both f of c, so f of c minus f of c over c minus c. If h is 0, then my denominator and my numerator are both 0, okay? So since we can't evaluate it with just the slope formula, now we think about our application of what we've been talking about the last couple sections, which is we stick a limit on there, okay? So what we are going to do is we are going to say, what is the limit as h approaches 0? So as h approaches 0, Q gets closer and closer and closer to point P, meaning our secant line approaches our tangent line. So if we can evaluate that as a limit, then we have the slope of our tangent line. Okay. Let's go back here. And now this is drawn without the dynamic representation here, okay, or the visualization. But really, this is what we're looking at. Oh, I use C on my representation here. It's in terms of A, but it doesn't really matter what letter we use. A is a constant, okay? The idea here is still that we find the slope of the secant line from point P to point Q, okay? And if we notice a plus h minus a, the a's cancel out, so we just have f of a plus h minus f of a all over h. By the way, these a's do not cancel out because they're inside the function, okay? This is a difference quotient that we saw in chapter 1 quite a bit where we were evaluating, okay? So we did some practice with that part already. The part that is new is adding a limit to there. So if we are looking for the slope of a tangent line at a point, then we stick a limit, okay? We stick a limit on the front of that difference quotient, and that's how we find the slope of the tangent line, which m sub tan is just a simplified way to write slope of the tangent. Okay, so it's the slope of the graph of the function at an instant, okay? And again, if we're thinking slope of a tangent, we also think instantaneous rate of change. All right, so I did a whole bunch of talking about the concept, okay, or like the visualization of where the slope of a tangent comes from. I'm going to do the examples in a second video because this is already long enough.